Prove that the efficiency of a Carnot's heat engine, the efficiency of a Carnot's heat engine, prove that the efficiency of a Carnot's heat engine is eta equal 1 minus T2 by T1. Eta is equal to 1 minus T2 by T1, where T1 is the temperature of source, T1 is the temperature of the hot chamber, and T2 will be the temperature of sink. That means T2 is the temperature of the cold chamber. A Carnot's heat engine consists of an insulating pad. A Carnot's heat engine consists of an insulating pad, a source at higher temperature T1 Kelvin, a source at higher temperature T1 Kelvin. That means the source is the hot chamber. And another chamber that will be sink at the lower temperature T2 Kelvin. And this is the cold chamber. A Carnot's heat engine consists of three components, that is source at T1 Kelvin, insulating pad, and sink at T2 Kelvin. And here T1 is greater than T2. That means temperature of the source is greater than the temperature of the sink. And this is a cylinder fitted with a piston. This is a cylinder and which consists of non-conducting vertical walls. This is a cylinder with non-conducting vertical walls, and a piston is set with the cylinder, and the cylinder contains ideal gas. The cylinder contains ideal gas. This is the ideal gas enclosed by the cylinder with the non-conducting vertical walls and conducting base. And this is what non-conducting vertical walls. Two walls will be non-conducting vertical walls, or the walls which encloses the ideal gas are non-conducting. This is the piston which is capable of moving in vertical direction, and the piston, frictionless piston, is fitted with the cylinder containing ideal gas. We can denote the different states or the initial pressure, volume and temperature. P1, V1, T1 are the initial volume, pressure and absolute temperature of the ideal gas. And the base is conducting. This is the conducting base of the cylinder. This is a Carnot's heat engine. Now we have to define Carnot's heat engine. What is Carnot's heat engine? That is, we have to describe. In this case, Carnot's heat engine is a heat engine. Carnot's heat engine is a heat engine which is operated through Carnot cycle, a Carnot cycle. And this Carnot cycle, the Carnot's heat engine is a heat engine which is operated through Carnot cycle, and this Carnot cycle consists of 4 stages. And this cycle will undergo through 4 stages, or this Carnot cycle consists of the following 4 stages. Number 1, isothermal expansion. Number 2, adiabatic expansion. Then the gas will undergo through isothermal compression. And the gas will return to its initial state through adiabatic compression, and the Carnot cycle will be completed. Carnot heat engine is a heat engine which is operated through Carnot cycle, and this cycle consists of the following 4 stages. Number 1, isothermal expansion. Number 2, adiabatic expansion. Number 3, isothermal compression, and number 4 is adiabatic compression, to complete one cycle or to return to the initial state of the gas. Now we can draw pressure versus volume graph, or we can plot The variation of pressure in terms of change in volume of the ideal gas placed in the cylinder. First, we shall show the isothermal expansion of the gas along the path AB. Along the path AB, the gas will be expanded isothermally. That means temperature remains constant from the point A to B, and at the point A, initial pressure, volume and temperature was P1, V1, T1, and at the final point B, pressure, volume and temperature will be P2, V2 and T1. In this case, temperature remains constant. Temperature at the point A was T1 and temperature at the point B becomes T2. During this expansion, during this isothermal expansion, the gas absorbs Q1 amount of heat energy. From the point B, we can draw a normal on the volume axis, and this normal is drawn at the volume V equal V2. That means at the point B, the volume increases to V2. Volume of the gas increases to V2. And now we can draw adiabatic expansion. And in isothermal expansion, the gas will undergo through isothermal expansion from the point A to B, and it absorbs Q1 amount of heat energy. And also the gas will undergo from the state B to C, in which adiabatic expansion will occur. The gas will undergo through the state B to C, and adiabatic expansion will occur. Now the gas will undergo through adiabatic expansion from the point B to C, in which pressure of the gas changes from P2, V2, T1 to P3, V3 and T2. Temperature of the gas changes from T1 Kelvin to T2 Kelvin. From the point C, we can draw a normal on the volume axis at the volume V equal V3. And this is adiabatic expansion. From B to C, the gas will undergo through the process adiabatic expansion. And now we can denote isothermal compression from the point C to D in the graph. The gas will undergo through isothermal compression from the point C to B. In this case, the state of the gas will change from the point C to D, in which pressure, volume and temperature of the gas will change from V3, V3, T2 to P4, V4, T2. In this case, temperature remains constant because the process is isothermal compression. And volume of the gas will decrease from the point V3 to V4, and this is isothermal compression. During this isothermal compression, the gas will reject Q2 amount of heat energy. Similarly, adiabatic compression will occur along the path dA in PV graph. Adiabatic compression occurs from the state D to A, that means from the volume V4 to V1. Now we shall find the work done by the gas during isothermal expansion along the path AB in PV diagram. We should consider isothermal expansion of the gas. We should consider isothermal expansion of the gas from the state A to B along the path AB. Let the cylinder be placed. Let the cylinder be placed on the source. Let the cylinder be placed on the source at the absolute temperature T1 Kelvin. capital T1 Kelvin, and let the cylinder be placed on the source at temperature T1 Kelvin, and the ideal gas in the cylinder absorbs a heat energy of Q1 Q1 from the source at the temperature T1 Kelvin. The gas expands from the volume V1 to V2. The gas expands from the volume V1 to V2 isothermally from the state A to B, and the work done by the gas in this isothermal expansion from the volume V1 to V2 at the constant temperature T1 Kelvin is given by work done by the gas in this isothermal expansion from the volume V1 to V2 is W1 should be equal to nR T1 log base E V2 by V1, log base E V2 divided by V1. W1 is equal to nR T1 log base E V2 by V1. This is the work done by the gas in the isothermal expansion, and this work done should be W1. In this isothermal expansion, the cylinder is placed on the source such that the gas in the cylinder absorbs a heat energy of Q1 from the source, and isothermal expansion occurs, and the piston fitted with the cylinder move upwards. That means there will be upward motion of the piston fitted with the cylinder containing ideal gas. Work done in this isothermal expansion from the point A to B is W1, which is equal to nR T1 log base E V2 divided by V1, where V2 is the final volume of the gas at the point B and V1 is the initial volume of the gas at the point A. Now we shall find the work done by the gas in adiabatic expansion. We should consider the adiabatic expansion of the ideal gas placed in the cylinder fitted with the piston. Now the cylinder is placed on the insulating pad such that its base is in contact with the insulating pad. The cylinder is placed on the insulating pad, and the gas will undergo through adiabatic expansion from the point B to C, that is from the state P1 P2 V2 T1 to P3 V3 T2. The gas expands adiabatically from the point B to C in PV diagram, and in this case the work done by the ideal gas placed in the cylinder fitted with the piston is given by the work done by the gas in this adiabatic expansion from the point B to C in PV graph is given by work done by the gas in the adiabatic expansion from the volume V2 to V3 is given by W2 as equal nR under bracket it should be T2 minus T1 divided by 1 minus gamma, under bracket T2 minus T1 bracket closed divided by 1 minus gamma. This is the work done by the ideal gas in this adiabatic expansion from the volume V2 to V3, and in this case temperature of the ideal gas will change from T1 Kelvin to T2 Kelvin. W2 is equal to nR T2 minus T1 divided by 1 minus gamma. Now the temperature of the ideal gas decreases the temperature of the ideal gas placed in the cylinder decreases from T1 Kelvin to T2 Kelvin. Decreases from T1 to T2. Now we have to consider isothermal compression of the gas from the point C to D in PV diagram. For isothermal compression, the cylinder which was in contact with the insulating pad at the temperature T2 Kelvin will be moved to sink at the same temperature T2 Kelvin. That means cylinder is moved from the insulating pad at the temperature T2 Kelvin to the sink at the same temperature T2 Kelvin and the gas rejects heat energy of Q2. The gas rejects Q2 amount of heat energy to the sink at the same absolute temperature T2 Kelvin. To the sink, the gas rejects heat energy of Q2 to the sink at the same temperature T2 Kelvin, and the gas compresses from the volume V3 to V4. The gas compresses from the volume V3 to V4 at the same temperature T2 Kelvin. In this case, temperature remains constant. For isothermal compression, initially the cylinder was placed on the insulating pad such that the base of the cylinder was in contact with the insulating pad and no heat energy is exchanged. And now for this isothermal compression, the cylinder is moved to the sink. Now the cylinder is moved to the sink such that the base of the cylinder is in contact with the sink. The cylinder at the temperature T2 Kelvin is moved to the sink at the same temperature T2 Kelvin such that the base of the cylinder is in contact. The base of the cylinder is in contact with the sink at the same temperature. Placed on the sink, the cylinder is moved to the sink from the insulating pad and it is placed on the sink. The cylinder, this is the cylinder in the diagram, which is placed on the sink such that the base of the cylinder is in contact with the sink, and in this case the ideal gas in the cylinder rejects Q2 amount of heat energy to the sink at the same temperature. Ideal gas at the temperature T2 Kelvin rejects Q2 amount of heat energy to the sink at the same temperature, that means at the same temperature T2 Kelvin. Therefore, the work done on the gas in this isothermal compression from the point C to D. In this isothermal compression from the point C to D in PV graph, from the volume V3 to V4, from the volume V3 to V4, from the volume V3 to the final volume V4, that is from the point C to D, is given by W3 is equal nRT2. W3 is equal nRT2. T2 is the temperature of the gas placed in the cylinder, log base E, V4 by V3. W3 is equal to nRT2 log base E, V4 divided by V3. That is the work done on the gas in the isothermal compression. Now we should consider adiabatic compression or adiabatic compression along the path DA, that is from the state P4 V4 T2 P4 V4 T2 to P1 V1 T1. The cylinder is again placed on the insulating pad. That means the cylinder containing ideal gas is moved from the sink at the absolute temperature T2 to insulating pad, so that the base of the cylinder is in contact with the insulating pad, and the gas compresses adiabatically. The gas compresses adiabatically from the temperature T2 Kelvin to T1 Kelvin. T2 Kelvin to T1 Kelvin. Therefore, the work done Therefore, the work done on the gas in this adiabatic or in this adiabatic compression from the volume V4 to V1, and from the temperature T2 Kelvin to T1 Kelvin. The work done on the gas in this adiabatic compression from the volume V4 to V1 is given by W4 as equal. W4 will be equal to, therefore W4 equal nr T1 minus T2 divided by 1 minus gamma. This is the work done on the adiabatic compression. Again, W2 is equal nr under bracket T2 minus T1 divided by 1 minus gamma. Therefore, the total work done in this Carnot cycle, on the gas is W equal W1 plus W2 plus W3 plus W4 equal W1 plus W3, since W2 is equal to minus W4. W is equal to W1 plus W3 since W2 is equal to minus W4. Therefore, putting the expression of W1 and W2, we get W as nRT1 log base C V2 by V1 plus nRT2 log base C V4 by V3, V4 divided by V3. This is the expression of total work done by the gas in the Carnot cycle. Hence, the efficiency of the Carnot's heat engine, is eta is equal to total work done by the gas in the Carnot cycle, work done per cycle divided by heat absorbed per cycle by the Carnot's heat engine. Eta equal to work done per cycle divided by heat absorbed per cycle. Therefore, eta is equal to W divided by Q1, where Q1 is the heat absorbed by the ideal gas placed in the cylinder in this Carnot cycle. According to first law of thermodynamics, we know that heat absorbed is numerically equal to the sum of change in internal energy and work done. That is, according to first law of thermodynamics, Q1 is equal to du, which is change in internal energy of the gas, plus work done W1 in the isothermal expansion from the point A to B in PV curve. Q1 is equal to du plus W1, or comma Q1 is equal to heat absorbed by the gas will be what? In place of du, we can write NCV under bracket T1 minus T1 plus W1. In this case, change in internal energy will be 0 because temperature remains constant in this isothermal expansion. So we get Q1 will be equal to W1, that is heat absorbed by the ideal gas placed in the cylinder of the Carnot heat engine, which will be equal to W1. Q1 is equal to W1, which is the heat absorbed by the gas in the isothermal expansion from the point A to B in PV curve. Therefore, efficiency eta is equal to W divided by W1. Efficiency is equal total work done W divided by work done in isothermal expansion. And here in place of W, we can write nRT1 log base C V2 by V1 and nRT2 ln or log base C V4 divided by V3 divided by nRT1 ln V2 by V1, ln V2 divided by V1. Ln means what? Log base C. And here efficiency of Carnot heat engine eta will be equal to 1 plus T2 divided by T1 into, in the numerator we should have ln V4 by V3 divided by ln V2 by V1. Ln means log base C. Of course, ln V4 by V3 is log base C, V4 by V3. and we get the expression of efficiency of Carnot heat engine as eta, which is 1 plus T2 by T1 into ln V4 by V3 divided by ln V2 by V1. In adiabatic expansion, that is from the point B to C, in adiabatic expansion, that is from point B to C, we should have T1 V2 to the power gamma minus 1, and at the point C we can write T2 V3 to the power gamma minus 1, where gamma is the ratio of molar specific heat of the gas at constant pressure and volume. In adiabatic compression, again in adiabatic compression from the point C to D, that means from adiabatic compression, that is from the point D to A, we can write T2 V4 to the power gamma minus 1 will be equal to T1 V1 to the power gamma minus 1, or comma you can write T1 V1 to the power gamma minus 1 will be equal to T2 V4 to the power gamma minus 1.